June 2003, a conference room at NASA's Goddard Space Flight Center. A team of astrophysicists is staring at a map, an oval of speckled color, red and blue patches scattered across a black background, built from data collected by a satellite called WMAP, the Wilkinson Microwave Anisotropy Probe. What they're looking at doesn't look like much, noise almost, static. But every dot of color on that map is light, real photons, captured by a real detector, orbiting a real point in space nearly 1,000,000 miles from Earth. And by the time those photons reached the satellite's sensors, they had been traveling for roughly 13.7 billion years. That number alone is almost too large to hold on to. 13.7 billion years is older than the Earth, older than the Sun, older than almost every structure in the visible universe. These photons left their source when the cosmos was approximately 380,000 years old. A toddler, cosmically speaking, glowing hot and opaque, just cooling down enough for light to finally break free and travel in straight lines for the first time in its history. And then that light simply kept going, uninterrupted, unblocked. Until, 13.7 billion years later, a spacecraft happened to be sitting in the right place to catch it. Here's the part that should stop you. By the clocks on Earth, by every calendar and timeline we use to measure the age of the universe, those photons are 13.7 billion years old. That's not in dispute. It's measured, mapped, cross-checked against multiple independent methods, published, peer-reviewed, awarded a Nobel Prize. But according to the photon itself, according to the physics that governs how light experiences its own existence, no time passed at all. 0 seconds. The moment it left the early universe and the moment it struck that satellite's detector are, from the photon's own perspective, the exact same instant. Not a long journey compressed into a blink, not a very fast trip. 0. As if the beginning and the end of a 13 billion year voyage happened simultaneously, in no time whatsoever. That's not a rounding error, and it's not a metaphor. It falls directly out of one of the most rigorously tested theories in the history of physics. And once you actually sit with what that implies, it forces an uncomfortable question that most explanations of light skip right past. If light experiences 0 time, if nothing about its own internal clock ever ticks forward even once, then what does it actually mean to say that light has a beginning at all? We talk about photons being emitted, created, born inside stars or particle accelerators or the fires of the early universe. We assign them birthdays. But something that experiences no time can't experience a before and an after. It can't experience getting older. So in what sense does it experience existing at a starting point rather than existing all at once everywhere along its entire path forever? Most people who've heard the phrase "light doesn't experience time" treat it as a fun fact, a party trick of relativity. Interesting, maybe a little spooky, and then you move on. But that's underselling what's actually going on here, because the full implication of this idea doesn't just describe light. It quietly undermines an assumption baked so deep into how we think about the universe that most of us never even notice we're making it. The assumption that everything which exists must have a moment when it started existing, and that whatever that moment was, it happened before now, in the past, the way every other event we know of happens in the past. Light breaks that, not by having a strange history, by not having one at all, in any sense a clock could measure. To understand how physicists arrived at something this genuinely bizarre, you have to go back more than a century, to a 16-year-old boy in Switzerland who had a habit of asking questions that sounded almost childish, until you tried to actually answer them. In 1895, Albert Einstein was a teenager attending school in Aarau, and he found himself stuck on a thought experiment he couldn't shake. What would happen, he wondered, if you could run fast enough to catch up with a beam of light? If you managed it, if you matched light's speed exactly, what would you see? According to the physics of the time, built on James Clerk Maxwell's equations for electromagnetism, light was a wave, an oscillation of electric and magnetic fields rippling forward through space. If you could run alongside that wave at the same speed, logically, it should appear to freeze. You'd be looking at a stationary ripple, a wave that wasn't going anywhere, oscillating in place forever. The problem was, Maxwell's equations didn't allow for that. A frozen electromagnetic wave wasn't a valid solution. It broke the mathematics that described how light was supposed to behave. Something in the picture had to be wrong, and young Einstein couldn't let it go. Not because it was assigned to him, because it genuinely bothered him that the universe seemed to be contradicting itself. It would take him another decade to fully resolve that contradiction, and when he did, in 1905, in a paper titled On the Electrodynamics of Moving Bodies, the resolution wasn't a small correction. It was a complete rebuild of how space and time relate to each other. Einstein's answer to his own teenage question was, essentially, you can never catch up to a beam of light. Not because you're not fast enough, and not because of some limitation of your rocket or your legs. It's because the very fabric of time itself behaves differently as you approach the speed of light, in a way that makes catching up mathematically, physically impossible for anything with mass. The closer you get to light speed, the slower time passes for you, relative to everything you left behind. Not slower like a clock running down, slower as in fewer seconds pass on your wristwatch, objectively, measurably, than pass for someone standing still. This isn't philosophy, it's been tested, repeatedly, with real experiments on real particles producing real, measured numbers. In 1941, physicists Bruno Rossi and David Hall climbed Mount Washington in New Hampshire to study cosmic ray muons, unstable subatomic particles created when cosmic rays slam into the upper atmosphere. Muons decay fast. Left alone, a muon's average lifetime is about 2 microseconds, 2 millionths of a second, before it breaks apart into other particles. Even traveling close to the speed of light, basic arithmetic says a muon shouldn't survive long enough to fall from the upper atmosphere, where it's created, down to sea level. The distance is too far. The particle should decay long before it arrives. Except muons do arrive, in enormous numbers. Rossi and Hall measured it directly, comparing muon counts at the mountain summit to counts at a lower elevation, and found far more muons surviving the trip than ordinary, non-relativistic physics could explain. The muons weren't breaking the rules of their own decay. Time for the muons, moving at a significant fraction of the speed of light, was passing more slowly than it was for the mountain, the detectors, and the physicists standing there with their notebooks. From the muon's own internal clock, barely any time had passed at all. From the mountain's clock, enough time had passed for most muons to have already died out. And yet, because of time dilation, a whole population of them survived the trip anyway. That was the first direct experimental confirmation of something Einstein had predicted purely from mathematics decades earlier. Time is not a universal metronome ticking the same for everyone. It depends on how fast you're moving relative to everything else. And it doesn't stop being true just because the speeds involved get more familiar. Every single day, satellites orbiting the Earth as part of the Global Positioning System carry atomic clocks precise enough to measure nanoseconds. Those clocks, moving at roughly 14,000 km per hour relative to the ground, experience time slightly differently than clocks sitting still on Earth's surface. A combination of their orbital speed and their distance from Earth's gravity well, both of which affect the flow of time according to relativity. If engineers didn't correct for this, if they treated the satellite clocks as ticking at exactly the same rate as ground clocks, GPS positioning would drift by roughly 10 kilometers a day. Not eventually, within 24 hours. Every map, every turn-by-turn direction, every emergency dispatch relying on GPS would become useless within a single day because the underlying assumption that time moves the same everywhere would quietly poison every calculation built on top of it. So this isn't some obscure corner of theoretical physics that only matters in thought experiments about teenagers chasing light beams. It's built into infrastructure you've personally used this week, correcting for a version of the same effect that let those cosmic ray muons survive their fall to Earth. Now push that same logic to its absolute extreme. Muons, moving at maybe 99% of the speed of light, experience meaningfully slowed time, enough to survive a trip they otherwise couldn't. GPS satellites, moving far slower than that, still need corrections measured in nanoseconds. The pattern is consistent. The closer something gets to the speed of light, the more dramatically time slows down for it, relative to an outside observer. The relationship isn't a straight line. It curves sharply upward as you approach light speed, described by something called the Lorentz factor, a number that starts near 1 at everyday speeds and shoots toward infinity as your velocity approaches the speed of light. Which raises the obvious next question: what happens at the speed of light itself? Not 99%, not 99.99%, all the way there. Here's where the mathematics does something genuinely strange. As velocity approaches the speed of light, the amount of time that passes for the object in motion, what physicists call proper time, approaches zero. Not a very small number, zero. And light, unlike muons or satellites or anything else with mass, doesn't approach the speed of light. It travels at exactly the speed of light, always, everywhere, the instant it exists. Which means, if you plug light directly into the same equations that explained the muons on Mount Washington and the clocks aboard GPS satellites, you get an answer of zero proper time, exactly, with no rounding involved. From a photon's own reference, if we can even call it that, and we're about to get into exactly why that phrasing gets physicists nervous, the moment of its creation and the moment of its destruction, however many billions of years apart those moments appear to an outside observer, are the same moment. No interval, no duration, no time passing whatsoever from emission to absorption, even if that absorption happens 13.7 billion years later in a satellite orbiting a planet that didn't exist yet when the photon was born. This is the fact behind that WMAP data sitting in that NASA conference room in 2003. The photons in that map traveled for 13.7 billion years by our clocks. By their own, 0. They didn't experience a long journey. They didn't experience a short journey. They didn't experience a journey at all, in the sense that a journey implies a beginning, a middle, an end, and time separating those three things. And this is where most explanations of this topic, the ones that turn it into a fun fact and move on, actually undersell how strange it gets, and where the real reality check comes in. The common way people phrase this idea is to say that light experiences no time, as if a photon has some kind of tiny internal perspective, sitting inside its own reference frame, watching billions of years pass by in an instant, like a passenger on the world's fastest, most disorienting train ride. That phrasing is everywhere, in documentaries, in pop science books, in casual conversations about relativity. And it's not quite right. It's not just an oversimplification. It's a description of something that, according to the actual mathematics of special relativity, doesn't exist at all. Special relativity's equations for time dilation and length contraction include, buried in their structure, a factor involving the speed of light and the speed of the object in question. Specifically, a term that requires dividing by something that becomes zero the instant an object's speed equals the speed of light. Division by zero isn't just a strange result. It's not a result at all. It's the mathematics refusing to produce an answer. The way a calculator gives you an error instead of a number when you ask it to divide by zero. There is no valid, well-defined reference frame for something moving at exactly the speed of light. Not a very strange one. Not one where time is frozen. None. The concept of a photon's own perspective, its own reference frame, its own experience of anything, isn't just eerie, it's mathematically undefined. A question the theory isn't equipped to answer. The same way asking what's north of the North Pole isn't a question with a strange answer. It's a question built on a premise the coordinate system doesn't support. So the myth isn't that light experiences zero time exactly. The myth is subtler and more interesting than that. The myth is the assumption baked into that phrase itself. The assumption that light must have some kind of experience, some kind of internal frame of reference, some kind of point of view, and that special relativity is simply telling us what that point of view looks like. It isn't. What special relativity actually tells us is that the entire question of what does light experience sits outside the boundaries of what the theory can meaningfully describe. It's not that the answer is zero, it's that there is no answer, because there's no valid frame to ask the question from in the first place. That reframing changes everything about how you should think about the beginning question we opened with. It's not that light exists in a kind of eternal present, aware of its birth and destination as a single simultaneous event. A strange but coherent form of experience compressed to nothing. That would still be a kind of experience, just an extremely unusual one. What the mathematics actually says is stranger and, honestly, more humbling. Our entire framework for describing beginnings, durations, and experience, the framework built on time passing, on before and after, on cause preceding effect by some measurable interval, simply stops applying once you reach the speed of light. Not because light is doing something exotic within that framework, because light exists at exactly the boundary condition where the framework itself breaks down. That's not a property of light, that's a boundary of physics itself, discovered by pushing Einstein's equations as far as they'll go and watching them refuse to give an answer once you get there. This matters far beyond a curiosity about photons, because it exposes something about how we think, by default, about causes and beginnings generally. We assume, almost without noticing we're assuming it, that anything which exists must have had a moment zero, a point in time, however far back, when it started, followed by a duration of existing, ticking forward like everything else we're familiar with. That assumption works perfectly well for you, for me, for planets, for stars, for essentially every object with mass that has ever been measured. It's such a universal pattern in our experience that we tend to treat it as a law of the universe itself, rather than what it actually is, a description of how things behave when they're moving slower than the speed of light, which is to say, everything we personally interact with every single day of our lives. Light was never obligated to follow that pattern. It only ever looked like it should, because we kept trying to describe it using language built for objects that experience duration, objects with mass, objects that move slower than light, objects for which before and after are always well defined. The moment you ask the same question of something moving at exactly the speed of light, the language doesn't just give a strange answer. It stops working entirely, and physicists have known this, carefully, precisely, since not long after Einstein's own 1905 paper, even though it took decades for cosmic ray experiments and later orbiting atomic clocks to confirm it wasn't just an artifact of the mathematics, but a real physical feature of how the universe actually operates. The consequences of getting this right, of correctly building relativity's stranger implications into real systems, aren't abstract. They show up as measurable, sometimes costly, sometimes safety-critical outcomes. That 10-kilometer daily drift in GPS positioning without relativistic correction isn't a thought experiment. It's an engineering fact that satellite systems have to actively account for, using the exact same equations that tell us light has no valid reference frame. Long baseline telescope arrays, used in radio astronomy to combine signals from observatories on opposite sides of the planet, have to correct for relativistic timing effects to synchronize their data correctly, or the resulting images blur into meaningless noise. Even particle accelerators, machines like the ones at CERN, which push protons to within a hair's breadth of the speed of light, have to be designed around the reality that as those particles approach light speed, their proper time slows dramatically relative to the lab, changing how long unstable particles appear to survive before decaying, exactly the way those Mount Washington muons did in 1941. None of this is optional or approximate. Get the relativity wrong, even slightly, and the technology built on top of it stops working, sometimes in ways that matter for navigation, for communication, for the basic infrastructure a modern world depends on, without most people ever thinking about why it works. Which brings this case file to where it actually stands today, because this isn't a settled historical curiosity sitting quietly in a physics textbook. It's an open thread that current research is still pulling on. Modern cosmology's entire picture of the early universe depends on exactly this strange relationship between light and time. The cosmic microwave background, the same radiation WMAP mapped in 2003, and which the European Space Agency's Planck satellite mapped in even finer detail starting in 2009, is, in a very real sense, a photograph of the universe as it existed 380,000 years after the Big Bang, delivered to us today by photons that, according to their own physics, never aged a single moment between then and now. Every time cosmologists study that background radiation to refine estimates of the universe's age, its rate of expansion, or the distribution of matter shortly after its birth, they're relying on the fact that this ancient light arrived essentially unchanged by the passage of time, carrying information from the early universe the way a signal that never degraded, never aged, simply persisted until something was finally there to receive it. And at the deepest level of current theoretical physics, this same boundary, the point where ordinary descriptions of space and time stop applying, sits at the center of some of the biggest unresolved questions in the field. Physicists working on quantum gravity, in frameworks like string theory and loop quantum gravity, are grappling with the possibility that space and time themselves might not be the smooth, fundamental backdrop Einstein described, but something that emerges from a deeper, stranger layer of reality, one where the ordinary rules of before and after, of duration and experience, might not apply any more cleanly than they apply to a photon. In other words, the exact same kind of boundary that makes it meaningless to ask what a photon experiences might be a small, local example of a much larger boundary sitting at the edge of everything physics currently understands about space, time, and the beginning of the universe itself. That question hasn't been resolved. It's actively being worked on, in papers, in experiments, in observatories still collecting light older than almost everything else in existence, trying to read the story of a universe that, in some sense, was never separated from its own beginning by any time at all. This is one case file. There are more discoveries like this one sitting quietly inside equations most people never look at twice. Places where the universe simply refuses to answer the question the way we expect it to, and the refusal itself turns out to be the real discovery. Subscribe, we are opening the next one.